Have you ever wished you could go back in time? Maybe you would want to fix a small mistake you made last week. Or, maybe you dream a little bigger, wanting to witness a great historical event, like the building of the pyramids in ancient Egypt. What if you could actually see what life was like when dinosaurs roamed the earth? The idea of traveling through time is honestly one of humanity's oldest and most powerful dreams. It captures our imagination like few other concepts ever can. It speaks to our deepest desires to understand our past and to know what our future holds. This question, is time travel possible, is not just for stories and movies anymore. It's actually a real question that scientists are exploring today. For a very long time, time was seen as something absolute and unchanging. It was kind of like a great river, flowing in one direction, from the past, through the present and into the future, at the same steady pace for everyone, everywhere. This was the view of Isaac Newton, one of the greatest scientists in history. In his world, time was a universal clock that ticked away uniformly for the entire cosmos. Then, at the beginning of the 20th century, a young patent clerk in Switzerland changed everything. His name was Albert Einstein. He came up with a revolutionary new way of looking at the universe. His theories of relativity, both special and general, completely shattered the old ideas about time. Einstein showed that time is not absolute at all. Instead, he revealed that time is relative. For centuries, time travel remained firmly in the realm of dreams and magic. It wasn't until the late 19th century that this idea took a giant leap forward. This leap was thanks to the English author H.G. Wells and his groundbreaking novel, The Time Machine, published in 1895. For the first time, the concept of time travel was presented not as a magical occurrence, but as a scientific and mechanical achievement. Wells's story introduced the idea of time as the fourth dimension. This shift from magical time slips to mechanical time machines marked a crucial turning point in our cultural understanding of the concept. This was the moment when time travel began its slow migration from the pages of science fiction to the blackboards of theoretical physicists. The door had been opened, just a crack, but it was enough to let the light of scientific curiosity shine on one of humanity's oldest and most cherished dreams. Einstein's first major breakthrough was his theory of special relativity. It was built on two simple but powerful ideas. The first is that the laws of physics are the same for everyone, as long as they are not accelerating. The second, and more radical idea, is that the speed of light in a vacuum is constant. This means that two people moving at different speeds will experience time differently. For the person moving faster, time literally slows down. If you could build a spaceship that could travel close to the speed of light, you could journey for what feels like a year to you, only to return to Earth and find that decades or even centuries have passed. Einstein's theory of general relativity presented an even more radical view of the universe. It proposed that space and time are not separate entities, but are instead fused together into a single, four-dimensional continuum. According to Einstein, this is exactly what massive objects like stars and planets do to space-time. They don't pull on other objects with some mysterious, invisible force as Newton had suggested. Instead, they warp or curve the space-time around them. This is not a theoretical idea, it is a measurable fact. The GPS satellites that orbit our planet have to constantly adjust their clocks to account for this very effect. Einstein's theory of general relativity told us that mass curves space-time, and we experience this curvature as gravity. This led to a startling question. What happens if you get a huge amount of mass and squeeze it into a tiny little space? The theory predicted that if the mass is dense enough, it will warp space-time so severely that it essentially tears a hole in the fabric of reality. It creates a region of gravity so powerful that nothing, not even light, can escape its grasp. This is a black hole. Near the immense gravity of a black hole, this effect of gravitational time dilation becomes extreme. If you could safely hover in a spaceship just outside the event horizon, time for you would pass incredibly slowly compared to someone far away. In 1963, the mathematician Roy Kerr found a solution to Einstein's equations for a rotating black hole. The Kerr solution was bizarre. It suggested that the singularity was not a point, but a ring. The theory implied that if you could navigate your spaceship through this spinning ring singularity in just the right way, without getting torn apart, You might be able to pass through the black hole and emerge somewhere else in space-time. Some interpretations even suggested you could emerge in another universe, or at another time in our own. This opened the door to a new, wild idea, using black holes as gateways through time. The strange possibilities hidden within Einstein's equations did not stop with black holes. Einstein himself, working with fellow physicist Nathan Rosen, discovered a solution that described a theoretical bridge connecting two different points in space-time. A wormhole, in theory, could connect two distant places in our universe. You could step through a wormhole in your living room and instantly appear on a planet in another galaxy, light years away. Because space and time are linked, a wormhole doesn't just connect two places in space, it connects two places in space-time. This means a wormhole could potentially link not only different locations, but also different moments in time. To build this time machine, you would first need to find or create a stable wormhole. Then you would take one end of it and accelerate it to near the speed of light for a while, then bring it back. You could then simply walk into the 2050 end of the wormhole and step out of the other end into the year 2030, effectively traveling 20 years into the past. This all sounds wonderfully simple, but there's a huge catch. According to our current understanding, wormholes, if they exist at all, would be incredibly unstable. To keep a wormhole open would require a type of matter that has properties we've never seen before. The most famous of these is the grandfather paradox. It is a simple thought experiment that reveals the deep trouble you can get into when you meddle with history. Here is how the paradox works. Imagine you have built a time machine. You decide to travel back in time, say 60 years, to a time before your parents were born. If your grandfather died before he met your grandmother, then one of your parents would never have been conceived. If your parent was never born, then you could never have been born either. And if you were never born, then who went back in time to kill your grandfather in the first place? This creates an impossible loop of logic. Your existence is required to go back in time and prevent your own existence. But if you prevent your own existence, you could not have gone back in time. It is a perfect contradiction, a causal loop that seems to have no resolution. Beyond the dramatic grandfather paradox, there are other, more subtle paradoxes that arise from the idea of time travel. One of the most intriguing is the information paradox, sometimes called the bootstrap paradox. Let's imagine a classic example. A time traveler goes to the future and buys a book containing all of Shakespeare's plays. The question then becomes, who wrote the plays? Shakespeare didn't write them, he just copied them. But the person who compiled the book also just copied them from Shakespeare's work. The information, the plays themselves, exists in a closed loop. It has no point of origin. The same problem can apply to a physical object. Imagine a scientist is given a schematic for a time machine by a visitor from the future. So, who designed the time machine? Nobody did. The design simply exists in a loop, created from its own future self. Physicists and philosophers have spent a lot of time thinking about this problem and have come up with a few fascinating potential solutions. One of the simplest ideas is known as the Novikov self-consistency principle. This principle suggests that the laws of physics simply forbid any action that would create a paradox. According to this principle, you can travel to the past, but you cannot change it in any way that creates a contradiction. The universe will conspire to ensure your actions are already part of history. In this view, you don't have free will to change the past. You only have free will to fulfill it. Another, more radical solution involves the idea of parallel universes, or the many worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event has multiple possible outcomes, the universe splits into different branches, with each outcome happening in its own separate universe. In this scenario, when you travel back in time, you do not travel into your own past. Instead, you travel into the past of a parallel timeline. In this new timeline, you can do whatever you want. You could kill your grandfather in this alternate reality, but it would have no effect on you because he is not your direct ancestor. Your own timeline where you were born remains untouched. So far, we have journeyed through the wild realms of theory, from Einstein's mind-bending ideas to the paradoxes that twist our logic. But what about the real world? Have scientists actually tried to test these incredible theories in a laboratory? One of the most famous experiments to prove time dilation was conducted in 1971 by physicists Joseph Haefel and Richard Keating. When the airplanes landed and the clocks were compared, they were no longer in sync. This Haefel-Keating experiment was a landmark achievement. It was a direct, tangible demonstration that time travel into the future is a real physical phenomenon. We see this effect even more dramatically in particle accelerators like the Large Hadron Collider at CERN. Scientists there can accelerate tiny particles, called muons, to 99.99% of the speed of light. At these incredible speeds, time for the muons slows down dramatically. They have a very short lifespan, but because of time dilation, they survive much longer from our perspective than they should, allowing them to complete their journey around the accelerator. These experiments are our first baby steps into the world of time control. They prove the principle is sound. Time is relative, and we can make it pass at different rates. If the physics of time travel is real, why haven't we built a working time machine yet? The answer lies in the colossal, almost unimaginable barriers that stand in our way. The first and most significant hurdle is energy. To travel into the future using speed, as described by special relativity, you would need to approach the speed of light. The energy required to accelerate a massive object, like a spaceship with a human inside, to such speeds is astronomical. It would take more energy than all of humanity currently produces in many years, all focused on one single object. We simply do not have a power source capable of this. The challenges for traveling to the past are even greater. As we discussed, the most plausible theoretical method involves a wormhole. But to create a stable, traversable wormhole, we would need something called exotic matter. Finally, there is the problem of safety and stability. Even if we could create a time machine, would it be safe? The forces involved in manipulating space-time would be immense. Furthermore, we still don't fully understand the laws of physics at these extremes. Our current theories, general relativity and quantum mechanics, don't work together perfectly. There is one more profound and unsettling argument against the possibility of time travel, and it doesn't come from a physics equation. It is a simple observation about the world around us. If time travel into the past is one day possible, and humanity survives to invent it, then where are all the time travelers? If people in the future can visit any moment in history, our time should be a popular tourist destination. But we see nothing. The silence from the future is deafening. This idea is a variation of the Fermi paradox, which asks why we haven't seen any signs of alien life if the universe is so vast. In this case, it's the paradox of the missing time tourists. Of course, there are other more creative explanations for this silence. Maybe time travelers are here, but they are operating under a strict code of non-interference. Another possibility is that time travel is only possible back to the point when the time machine was first invented. If a machine is built in the year 2500, it might only be able to travel to points between its creation and the future, but not to any time before 2500. Perhaps the many worlds theory is correct, and any traveler from the future would arrive in a parallel version of our past, not our own. But let's step back from the physics for a moment and ask a different question. What if we succeeded? What would it truly mean for humanity if we unlock the secret to moving through time as easily as we walk down the street? The power to travel in time would be the most transformative technology we have ever conceived, far surpassing the invention of fire, the wheel, or the internet. Imagine historians no longer having to piece together the past from dusty records and archaeological finds. But this incredible power would also come with unimaginable responsibilities and dangers. If we could change the past, who would decide what changes to make? As we stand here today on May 24, 2024, the dream of time travel remains just that, a dream. It is a beautiful, tantalizing idea that lives at the very edge of scientific understanding. The journey has taken us from the myths of our ancestors to the mind-bending equations of Albert Einstein. We have explored the practical realities of time dilation and the theoretical fantasy lands of wormholes and closed time-like curves. The path forward is uncertain. The obstacles, from astronomical energy requirements to the need for undiscovered forms of matter, are immense. So, is time travel possible? For now, the answer is a firm maybe. The future is an unwritten book, and the final chapter on time has yet to be penned. The dream is still alive in the minds of physicists, in the pages of our stories, and in the heart of anyone who has ever looked at a clock and wondered, what if? The quest continues, driven by that most powerful of human traits, curiosity. And it leaves us with one last grand open question that will echo through the ages, waiting for an answer from a future we cannot yet see. If we ever do unlock the secrets of time, what will we choose to become?